Good morning. My name is Tariq Abdoun. It's a pleasure to be here. Thank you very much for inviting me. I'll be talking today about a project which we have in the US, which I see a lot of connection with urban flood, and we are interested in possible collaboration, so I thought it would be a good chance to come here, show what we are trying to do. This is a project which have been supported by NIST, which I'll mention what's NIST in the US, which is really for developing a multi-scale monitoring and health assessment framework for controlling and effectively health assessing and monitoring the infrastructure, flood control infrastructure in the US. This is a multi-principal investigator as well as multi-institute project led by Professor Zegal with me, who's doing the health assessment. I'm dealing mainly with field sensors, and we have people who are dealing with satellite imagery as well as industry. It's a very important part of that collaboration. It's a 4-year effort in the US. NIST, it's a federal agency in the US. It's really focused on the state of the art, of pushing the state of the art of technology and making sure it finds its way in industry in the US. So one of the main aspects for it is really have to be high risk, high reward kind of research. Otherwise you can't make it over there. So you really have to show what's the state of the art and how we are pushing that to the next step or the next generation before you be able to be supported with this program. We have in this program, we're collaborating also with the US Army Corps, who are providing us with the sites which we can monitor and basically start collecting data and so on to kind of prove that the system we're developing is working and is being implemented. This is a vision. I'll take a minute or two to kind of explain. If you look at the title, it's explaining what we are trying to do when we talk about multi-scale and effective. It's really, hopefully you can see that in the vision of what we are trying to do. With distributed network like levees, it's always a large number or distributed in a very huge area. So you have, for example, in the US, you have several hundreds of miles just in New Orleans, which you need to monitor and assess continuously. So going back with people going on the levee and looking at it is not the effective way of doing it. And again, this is a surface not really giving you an indication what's happening inside the levee. So the system which we are proposing and developing really starts by looking at the global performance of the network using satellite imagery. There is new technology which we are developing which will allow you to monitor this several hundred of levees to the accuracy of a millimeter in terms of deformation in that levee. So you have a first-hand assessment of your network. You can start identifying location which is sustainable or which is performing well, some other areas which are kind of starting to show distress and approaching failure. With this kind of information, you can go start implementing more localized instrumentation. We have developed instrument which we call shape acceleration array, which can measure this. This has been a successful implementation before here in the Netherlands and other places. We are building on that success and basically go to these local areas and we can put into the ground actual instrumentation and look into. An intermediate link between both, we're also developing GPS units, which is high resolution, low cost GPS units, which you can put it also in other areas which there might be some concern or validate some of the data you're getting with the satellite for kind of validity. So this is kind of an outline or a vision of what we are trying to do in terms of instrumentation. The same thing we are doing with health assessment. Based on this data which we are collecting, you might have an indication something is moving, but that doesn't tell you without understanding the system if that's approaching failure or not. So we're linking that with the health assessment techniques which Professor Zegal does to kind of give the decision makers enough information to decide if there is evacuation required, there is a remediation needed, or whatever, but they have all the tools they need to make that decision. So this is just a quick outline of my presentation. Again, there is a lot of things we need to do. It's a 4-year project, but I'll just highlight some of the different development, different levels. As I said, we are trying to provide a comprehensive framework for decision makers about the management and safety of the levee. We are doing that by developing a monitoring system and building some of stuff. So we are not only using sensor technology, but we are developing some of the stuff which we feel we need and doesn't exist right now, or we can do it better. So developing INSAR, which is satellite imagery, some of the stuff we are doing, low-cost GPS, shape acceleration, plus pore pressure, which we are adding to get all the information we need about levels. Data collection, data management, which is a big part. We have the industrial partner who is in charge of that part. I'll be talking about it. And finally, the health assessment of sensors. Start by the satellite imagery. There is a lot of different satellites out there, commercial, which you can get their data. It's relatively, compared to what you get from the satellite, it's relatively cheap. You can get an image of an area up to 50 by 50 kilometers for something over the years. For us in the US, it's expensive. For you, it might be much cheaper here in Europe. It's about $50,000 to monitor the whole system for a full year. In Europe, because the satellites we use, actually the European satellites, the US doesn't have commercial satellites, it's almost free to get these images. So it's a matter of how to process it and how to use it. There are several different types of satellite imagery which you can use, different bands. Each one have its own abilities. Some of them are useful when you have high bushes or trees. It can have a potential, which is the L band, which can penetrate through it, but the accuracy is not that good. Other cases where you have less penetration, so in cases like New Orleans where they don't allow having implementation on it and so on, X-band would be a best option for us, and that's what we are looking at. It will give you very high accuracy. On the other hand, we are not only looking at deformation, but we're looking also at information about the moisture content. So for moisture content, something the L-band would allow some penetration in the ground and give you some ability to also detect the moisture content near the surface of your levee system. So what we are planning to do is basically start with the X-band to get the accurate movement or deformation in the levees. Then we do other analysis with L-band to get the moisture content in phase 2 of our project, which is in the second year. One of the satellites we are working on, which is, or considering, is TerraSAR satellite, which is, I think, is German satellite, and it has the ability of collecting with both, so it can meet both of our demands. Again, when you look into INSAR technology and the way you're processing, this is some of the work which have done before. We're basically looking at New Orleans area, and you can see each pixel here on this is basically giving the history of deformation or settlement over the last 4 years on the New Orleans area. So basically each point here gives you what settlement. If you pick one of the points, it gives you how that have been settling over a period of 24 months. So with that, you can identify quickly the points, for example, which are red dots here. They have been exerting excessive amount of deformation. You can go start implementing something in more details and monitor that. When you're dealing with satellites, again, there's different modes of how you scan, what we call strip mode, which again, you're going over a strip, so if it's something longitudinal, you can go over that area and scan it. And with that strip mode, you basically can cover an area of 30 by 50 kilometers, and you have a certain accuracy. Each pixel is about 3 meters. When you are looking at spotlight mode, which is this one, we're focusing on that one, your resolution is about 1 meter in terms of pixel on that image is 1 meter, but the area you're covering is about 5 by 10. So again, you see what you're trying to do and pick whatever is most suitable for your application. GPS, again, there is a lot of technology. There is some of it is very accurate, but it's very expensive. So one of the things which we are set to do is you have some GPS unit, but in the range of $12,000 or so to give you the accuracy you need to do an actual engineering assessment of the levee. That's too expensive for wide implementation. We are collaborating with our partner Measuran, where basically we are developing using the low cost, low resolution, and basically through the algorithm of processing the data on it, being able to make it performing as a high resolution, high cost. And actually we have the first prototype ready for implementation this December with that new system. Where basically we're bringing it down to about $1,000 or so, while you're getting the same accuracy with 1 millimeter accuracy. Okay, so this is some of the development we are trying to do. Another one which we are building, which is what we call shape acceleration array, that was developed in the US in 2004, where basically it's a robe, it's a flexible robe, which you can put in the ground. It can measure for you the 3D deformation, so X, Y, and Z, at every 30 centimeters. So if you put it down in the ground up to 100 meters, you can get the deformation at each point, X, Y, and Z for it. You can get the temperature, you can get also the acceleration. So it provides you with more or less most of the information you need. The only thing which was missing was being able to get pore pressures. And that's what we are doing in that project, adding to it the ability to measure pore pressure. This is just a vision of what it can do. You can put it in slopes, foundations. It's a 3D, so you can put it vertical or horizontal. And this is actually a picture of it. It's pretty flexible, so basically you can even, so it's really like a rope, so you can even roll it on a really as a system. This system have been used excessively. I couldn't resist being here in the Netherlands and not talk about the IDAC, which we had the pleasure to work with the group here on it, Andre and Daltros. And basically, the system was implemented in it. Actually, it was used in the early stages for measuring the consolidation of the peat, because there was difficulties to kind of estimate that. And actually, it was used in the actual IDAC levee as a reference for deformation of levee failure. And you can see this is a progress of failure that happened. This line here shows the failure, which went about 2.5 meters or so. It didn't fail, it's continued because it's very flexible, but if I show the 2.5 meters, you're not going to see this. So for scaling, I'm just zooming on part of it, as this is actually the actual test in New Orleans, in IDAC. We had other applications for it. This is a famous case. We had used a shape acceleration array. Actually, we used it as a monitoring system, early warning, and for Minnesota DOT, where basically they got a warning from the system indicating there is excessive movements. And they had to close the highway because it was excessive, and within 48 hours, the highway collapsed. So this is a kind of monitoring we are trying to provide also for the levees. So learning from the experience, being able to monitor things continuously and provide information which is allow you to make decision of evacuation, closure, or whatever in real time and react to it. So what we are trying to add to it or implement, beside being able to measure deformations and acceleration and temperature, now we're adding the ability to measure pore pressures at different applications. And again, our project started 8 months ago. So again, the plan is to have the first prototype available by December for the early implementation in the spring in New Orleans area. Right now, we have selected 4 different locations for the early implementation in New Orleans. The idea is to select these sites based on satellites, but again, we need to start collecting data. So these sites were selected based on the engineers on the site, what they have problem with, their experience, so that we'll start monitoring these areas, and as the satellites start collecting data and give more information, we might add some additional site to that application. Some of the sites we selected are new construction sites which didn't have levees and we're placing them, so you're expecting a heavy or large deformation due to that new construction. We're implementing the shape tape in vertical location. Also, you can place it horizontal and get the profile of the settlement at different locations. With it, that's an application we use for bridge embankment. So we are going to be selecting the sites, again, new sites, some cases where you have some of the levees are earthen levees and connecting with structures. So usually when you have different systems, you have vulnerability of different performance and problems. So areas where you have 2 different systems meeting how you are going to implement it. They have issues here with different settlement of the levee, earth levee, which is different than the structures they are worried about forming gaps. So basically, we are trying to collect data which is useful for the engineers at the site at this stage and help us start implementing our framework. Data collection, data management, which is a challenge. We are dealing from satellite imagery and very complicated system to sensor data. We have our partner, which is Geocomp, which will be collecting this different information and develop a warning system, or what they call IC Central, which basically designed to handle multiple data, make sense of it, and being able to provide that on the internet to decision makers and basically able to warn them in real time about the result of the system. So they are working with us closely. Geocomp, for some of you who might not know it, they are the biggest US company which deals with data monitoring and health assessment in the US. They dealt with projects like the Big Dig in Boston, several $1 billion and so on. So they are well suited and have a lot of experience in terms of industry in helping us managing our data sets. The second phase, which is basically making sense of all this information. You have a lot of data, a lot of information. How do you process it? That's where Professor Zigals comes into picture. And we are doing the monitoring or health assessment as multi-scale as the instrumentation. So as we are collecting the low resolution, which is every 3 to 5 meters satellite imagery, we're basically doing inverse problem system identification. We're basically taking this data, trying to estimate what's the scenarios which allow, or failure scenarios in the levee which create this kind of deformations. So you're basically using the information about each point, doing the consistent model or the modeling of the system, being able to predict what would happen in the internal nodes and compare them with the measurements. And you do that in an iterative process. When you get a balance of the system, or there is no external forces between what you predict and what you measure, then you reach stability. And then you identify what the scenarios are and what's the possibility of failure. As I said, we do that in different stages. If we go to the high resolution sampling rate, which will give you every 1 meter, basically you have a levee every 1 meter you have an information, or every 3 meters you have surface information about how it's deformed. That's a lot of that. And again, take the same thing, being able now to get in more details using the surface deformation to estimate the scenarios why the system is generating this deformation and what's the mode of failure. Is it a sliding slip? Is it failing due to foundation bearing failure? Whatever scenarios which create this kind of deformation, surface deformation. The third level, which we are talking about, is again for problematic areas. You can now implement the shape tape acceleration array, measure deformation, measure pore pressures, and do a more detailed analysis about how the system is corresponding. So we are doing that in real time as the data comes with the 3 different levels, and use that to guide the decision of if there is any necessary need to evacuate or repair a system. This system have been tested, not in levees but in other applications. We have implemented that system in California for a wildlife site where basically the concern about seismic hazard. We're basically implemented several arrays, and you are doing a full-scale test in this case, because between the soil between these arrays is basically your tested system. And what we do, we have what we call a T-Rex, which is actually a truck which goes there. It's a very massive truck. It generates earthquake at your site. So basically, we didn't wait for it to happen. We implement the system. We bring that. We know the profile, and that's what you have, and we are trying to predict it. And I'll show you in a minute. So basically, we apply the same system. And this is actually the case where we are shaking it. If you pay attention to the soil, it starts liquefied, acting as if it's a jello. And basically, that's what you get during an earthquake. So you generate the deformation. Again, could be in case of floods, it could be from the flood and rain season. And as long as you have a deformation, you can start back figuring the soil properties. So what we did, as we generate this deformation, we use this data and start with any random property for the soils and let the system predict what's the actual property. So we start with that black line, And you can see we started with one estimate for everything, and the system was able to predict the 3 different layers with the 3 different shear modulus for it, based on the actual measurement and correcting itself as it goes. This is what we started, or that's a real property. That was estimated by the system which Professor Zigal developed. So you get very close to reality based on the actual measurement of the system. So anyway, this was my last slide. Hopefully I gave you an idea what our project is all about, and I hopefully see the link and the possible collaboration with Urban Flood, which I think would be a nice complement to each other. Thank you very much.
Questions for Mr. Abdul?
Thank you. That was very interesting. I was just going to ask, when you install this, you call it a rope or wire, or it was fairly thin, wasn't it? It was, yeah. Do you need to account for any very localized changes that are occurring around the wire? So if fluid came in and fluidized around the wire, or the wire moved, how do you account for small effects that are occurring around the wire and not inferring that to being the overall?
There is 2 different methods which you can install with, which basically you can push it into the ground and push it directly in the ground, and then the soil closes on it because you are putting it very deep. If there is any issues similar to what you are talking about, would be very shallow near the surface. Deep into the ground, the soil closes, there is very high confining pressure, so there is not really much concern about that. And we usually are interested in the deep, more than 1 meter into the ground kind of behavior. Other cases which some people like to do because they would like to retrieve it and use it for another application, which basically you put it in a very thin flexible tubing and grout around it. So people put their array in, do their measurement. After they are done with it, they take it out and apply it, use it for some other applications. So it depends how you want to implement. But actually in this one, the one I showed for the wildlife case, which is in California, some of the arrays were put into the ground directly, some of them put into a casing, because we were interested to see if there's a difference in performance, especially when you're measuring vibration and you want to make sure that the sensor is in a good connection with the soil because you're measuring accelerations, and both gave the same response.
In all axes?
In all axes. And actually, in that site, that's the most instrumented site in the US for seismic, there was other instrumentation which put into the ground, which we compared with. Okay. And the interesting thing, the original instrumentation for that site was about $1 million to put about 50 sensors in the ground. With our system, for about $50,000, we doubled that 3 times. So went from 50 to about 200 sensors in the site for a fraction of the cost. So that gives you how much instrumentation is improving with time. That was instrumented 10 years ago, and now it's much cheaper.
Also,
Just a second. Yeah.
Any local changes that are induced by these arrays are not going to have any significant impact on the global behavior. And actually, that's what we're looking for.
I was going to say you need multiple arrays.
Well, you need, anyway, for the analysis, you need multiple arrays. And then it's about, the analysis is about comparison. I mean, to put it lightly or to put it simply, the analysis is about comparing what each one of the sensors is doing. In any local effect that is induced by the process of putting a sensor in the ground is not going to have some impact on the analysis. So you end up really not affecting the conclusion. Yeah.
Okay. I have a question in the back, Valeria.
So, my name is Valeria Grzanowska and I work for the Urban Flood. I'm very much impressed and surprised to see that indeed our projects have lots in common. And I'm working on the modeling part. And in your presentation it is somehow hidden, all this model-based assessment. So I would be very much interested to talk to you or maybe to your colleagues about the modeling simulation, which tools you use, which models you implement, discuss this. Sure. Okay. Yeah. So we have a couple of presentations at the end of the day, like 4 p.m. So I hope one of you is still around to communicate. Okay, great, thank you.
Okay, thank you, Lyra.
Hello. I have quite a few technical questions as well, for which I will approach you separately. But for now, a more organizational question, because it comes across as quite an effective collaboration between private companies, universities, knowledge institute, and perhaps some government sponsors. I'm very interested on how that is set up and funded in the US. Maybe we can learn from that.
As I mentioned, this initiative which we participated in is really focused on making sure the technology reach industry and helps the US industry flourish. So we couldn't, as an institute, apply for it if we don't have industrial partner. So in our case, which was a nice collaboration, this company, because we do a lot of field monitoring and testing, we have been working with them for a very long time. They have done research. There are some companies in the US, because of tax benefits, they are interested in funding research. And this is one of the few who does that, and they have a very active research component of their company. So we had a long working relation. When we saw this project, we felt this is a very natural match between our expertise and their expertise. So it's not trivial, it's not easy, but the fact that we have a working relation, they are interested in research, they understand research environment. We have been working a lot with industry, so we have an understanding what deliverables are, what deadlines are, not like typical research where we can go for a long time in research. And that's what makes the industry nervous. That's why there was a good collaboration, and I think that's a key for the success of that funding was the collaboration.
And are government assignments involved in that as well? Is there an active interest?
That's the US Army Corps, which basically they are interested. One of the things which benefits from their participation, certainly access, as well as they are going to be the stakeholders who use this data. So their input about what we should have as a final output for them to help them make their decision is very crucial. Otherwise, we develop something which is they don't like or they don't utilize, and we didn't achieve much. So their feedback from the beginning is very important.
Any more questions? No. Two of them.
I would like to know the lifespan of the different system, different sensors.
You mean the sensors themselves? Yes. Again, we have implementation now on the ground for more than 5 years, and there is no problem. So as we design them that they will last 15, 20 years. But for the implementation we had now, we had implementation since 2002. They are still in the ground and performing perfectly.
Interesting. Rob? Yeah.
Yes, I was wondering, you were telling about the test. You had initial estimates of the soil strength. Then you did the tests and you got soil strength from the test results. Did you compare them with common laboratory tests?
No, in this case, actually, the aim of that project was basically using the field test to kind of substitute the need for the lab test. Because in many cases, when you take a sample, it's so distorted, it really doesn't represent what you have in the field. And I think that's one of the cases in IDIC when we had to do the test in the field to get the real compressibility, because when you take a sample, it doesn't, sand is the same way. It gets distorted. So the aim of that project was to show with the proper instrumentation, you can use that as your lab test, and you don't have to go take a sample and do a test in the lab. So that actually was the aim, is to show that you can replace it. And now instead of having this triaxial sample, which is 2 inch or so, you're basically using this massive soil of your site, and you basically getting the characteristics of that site. Okay.
Okay. I think we have had enough questions. Thank you very much, Tarek.